Hey guys, and welcome back to another calculus video. In this video, we are going to talk about limits, and we're going to look at indeterminate forms of limits, and we're going to add another tool to our tool belt to help us figure out the determinant for the value for an indeterminate form, and that's going to be L'Hopital's rule. So when we talk about indeterminate forms, we're talking about forms that end up being 0 over 0 or infinity over infinity. And some things that we've seen in the past. So we've seen stuff like this. With this first one, if we want to take the limit as x approaches -1, we're going to have 2 times -1 squared minus 2 over -1 plus 1. This is the indeterminate form 0 over 0. And a technique we saw back at the beginning of the course was factoring and reducing, and then taking the limit again. So we could factor a 2 out, and if I factor a 2 out here, that's going to leave me with x squared minus 1, which factors into x plus 1 times x minus 1. And you can see how those x minus 1s cancel in the top and bottom. And now we're really taking the limit as x approaches -1 of 2 times x minus 1. And now if we substitute in our -1, we're going to get 2 times -2, which is equal to -4. So we would say that limit is -4. This one we saw when we talked about limits at infinity. We're in the form of infinity over infinity. So we said the technique we could use was looking at the denominator and dividing by the x value with the biggest exponent. So we're going to divide everything by x squared in the top and bottom. And then we're going to reduce that. So we're going to have 3 minus 1 over x squared over 2 plus 1 over x squared. And we said as x gets larger and larger, both of those fractional pieces are going to 0. So this limit is heading to 3/2. So those were some tools that we talked about, but now we're going to add another one. Before I talk about that other one, let's look at this example. If we were to go and take the limit as x approaches 0, we're going to end up with the indeterminate form of 0 over 0 again. Even though this is not an algebraic expression like that first one we talked about here, we could still use algebra to simplify this. That top factors into e to the x minus 1 times e to the x plus 1. Remember when we multiply and we have the same base, we would add the exponents together, so you can see how multiplying this would give me that. So it's really a difference of squares. And then we can reevaluate that limit, even though it had transcendental functions in it. We're going to get 2. But what if we had a mix of transcendental functions with just basic algebraic functions like this guy? So we end up with 0 over 0 in this case. There's not a way that factoring and reducing would help us in this problem. We could still factor the top, but nothing's going to reduce with the denominator. So we need some kind of tool to help us be able to figure out what that limit's going to be. Even if we were to split the numerator, notice we would still not be able to simplify anything. And this is where L'Hopital's really shines. It will help us figure out what those limits are going to be. L'Hopital says that if you are in the indeterminate form, 0 over 0 or infinity over infinity, and it could be positive infinity over positive infinity or negative infinity over positive infinity, any variant of that, then we can reevaluate the limit after taking the derivative of the top and the derivative of the bottom separately. So this limit is going to be the same as the limit of the ratio of those derivatives. So let's go back to this one and see if we can apply that. We're going to take the limit as x goes to 0. So we're in the form of 0 over 0. We're going to take the derivative of the top. The derivative of e to the u is e to the u times du. Derivative of 1 is 0. And the derivative of x is 1. Notice this is not the quotient rule. It's the derivative of the top and the derivative of the bottom separately. And then now we're going to reevaluate that. When I plug 0 in, I'm going to end up with 2. So there's my limit for that one. Now, even if we were to split this, we would end up with an indeterminate form. There are other indeterminate forms, but notice this would be infinity minus infinity here, and we could verify that by looking at this in the calculator. What happens is the x goes to 0. This guy is going to get really big because of this. That's growing much faster than this. And then we know 0 is a asymptote for this guy, a vertical asymptote to be specific. So we would be approaching infinity or negative infinity there too. So you can see how, depending on if we're going from the left or the right. So you can see how this is an indeterminate form, infinity minus infinity. And we're going to talk about all the indeterminate forms in this. So what are those indeterminate forms? 0 over 0, infinity over infinity, and then you have a few more. Infinity minus infinity, 0 times infinity, 0 to the 0, 1 to the infinity, and infinity to the 0. So we're going to have different techniques to help us work through these, but we're going to use L'Hopital's for all of them. The goal is to rewrite these so that I can use L'Hopital's. I can only use L'Hopital's if I'm in the form 0 over 0 or infinity over infinity. So if I'm already in that form, I can just go ahead and apply L'Hopital's. If we're in the form infinity minus infinity, like we were in that previous example, this is usually when we have a fraction minus a fraction and both fractions are going to infinity. Your trick is going to be to combine the fractions. If we're in this form, 0 times infinity, we're going to do a clever rewrite. We're going to rewrite it so we end up getting 0 over 0 or infinity over infinity. And then we'll be able to apply L'Hopital's rule. These three are going to have issues in the exponent, which means we're going to have to set the limit equal to y. And then we're going to take the ln on both sides. And then we can do some manipulations to help us solve that one. Sometimes we may have to do a clever rewrite. Forms that are not indeterminate, which means that they are determinate, which means we know where they're going. If I have infinity plus infinity, so if I have two fractions and I'm taking the limit, and I know the first fraction goes to infinity plus the second fraction's going to infinity, if I have two numbers that are just larger and larger without bound, then that sum is going to get larger and larger without bound. Same thing's true if I'm going in the negative direction. 0 to the negative infinity is going to go to infinity, and 0 to the infinity is going to go to 0. You could think about this one, that negative exponent, writing it this way. So this guy is an issue because we can't divide by 0, which means we have a vertical asymptote here, which means we have unbounded behavior. So let's look at a few examples. This first one, limit as x goes to 0 of e to the 2x minus 1 over x. We did this one just a minute ago, but just to recap this, if we were to plug in the 0, we're going to end up with 0 over 0. So we're going to apply L'Hopital's. E to the u is e to the u times du. The derivative of 1 is 0. The derivative of x is 1. And now if I plug in 0, I'm going to get 2 for that limit. Next one, limit as x approaches infinity of ln of x over x. If I plug in infinity, the limit as x gets larger and larger, the ln as x gets larger and larger is going to go to infinity, and that bottom is going to go to infinity. So I can apply L'Hopital's. Derivative of the top is 1 over x. The derivative of the bottom is 1. So I'm thinking about that x getting super big. I'm going to represent that this way. So as the denominator gets larger, the whole fraction is shrinking. So it's heading towards 0. Let's look at this one. We want to know what happens as x heads to negative infinity. So if we were to plug infinity in, if I take negative numbers and I square it, I'm going to end up with positive numbers. If I look at what's happening here, I'm plugging in negative numbers, which means that exponent is going to be a positive, which means that that denominator is growing without bound. So that's heading to infinity over infinity. So I can apply L'Hopital's. Derivative of the top, derivative of the bottom, and then we're going to apply this again. If I look at negative numbers and I plug it in, that numerator is going to negative infinity. If I plug negative infinity down here, so I'm looking at super small numbers like negative 1 billion or negative 1 trillion, I'm going to have a positive exponent here. So e to a positive exponent is going to grow without bound, but because it's negative, it's going to head towards negative infinity. So I get to apply L'Hopital's again. What's nice about L'Hopital's is that as long as you get 0 over 0 or infinity over infinity, you can keep doing it. Derivative of the top, derivative of the bottom. And now if I think about those negative numbers and I plug it in, negative negative would make that a positive. So this is getting super large, so that whole fraction is getting super small. Let's look at another example. We have the limit as x approaches infinity of e to the negative x times square root of x. So if I think about what happens as x gets super big, this guy is going to head to 0, but this square root's going to head towards infinity. So this is in that indeterminate form, 0 over infinity. So let's rewrite this. I could move that term with the negative exponent to the denominator, which would make it a positive exponent. And now, if I plug in infinity, I'm in the form infinity over infinity. So I'm going to take the derivative of the top, derivative of the bottom, I'm going to rewrite this so that it's 1 over 2 square root of x divided by e to the x. When I divide fractions, I do keep change flip. And now as x gets large, that whole fraction gets really small. Let's do another one of that type. Suppose I have the limit as x approaches infinity from the right of x times ln of x. So we think about what the ln function looks like. Your ln function has a domain issue as you approach zero, you've got that vertical asymptote there. So if we were to plug zero in, this would be in the form 0 times infinity. So we would need to do a clever rewrite here. Here's your trick for this clever rewrite. We're going to have ln of x, and we're going to divide it by 1 over x. Why? Because if I look at what's happening here, when I plug 0 into the top, as I approach 0 from the right, I'm heading down to negative infinity. And as I approach 0 from the right of 1 over x, here's what 1 over x looks like. 0 from the right is going to head up to positive infinity. So now I'm in the form that I can use L'Hopital's. ln of x is 1 over x. And then I could rewrite this. This is really x to the negative 1. So I'm going to write it as negative x to the negative 2. We're going to have to manipulate this. Negative divided by negative is a negative, and we subtract the exponents. It's going to be top exponent minus bottom exponent to simplify that. I'm going to get negative x there. And as I approach 0 from the right, the value of negative x is going to go to 0. So there's two examples for that particular form. Now let's look at 1 to the infinity. The ones where you have something in the exponent. There's three forms that we had talked about. 1 to the infinity, 0 to the 0, and infinity to the 0. They're all going to work the same way. Here's our process. If we plug in infinity, we're going to have 1 plus 0 to the infinity. So we're going to set this equal to y. And then we're going to take the ln of both sides. So I'm going to take the limit as x approaches infinity. I'm going to have the ln of 1 plus 1 over x to the x. So if you remember back in the limit chapter, we took a look at all the properties for limits. And one of the properties says if you take the ln of the limit, it's the same thing as taking the limit of the ln. So you can interchange those. And we're going to use that fact here. So we're going to bring that exponent down. So now if I look at what's happening here, this is going to be infinity, and the ln of 1 as x approaches infinity. It's going to head towards 0. Having technical difficulties here. So I'm going to take the limit as x approaches infinity, and I'm going to rewrite this limit as 1 plus 1 over x. And instead of using x here, I'm going to do 1 divided by x. Because now, as x goes to infinity, this is heading to 0. ln of 1 is 0. And as x goes to infinity, that denominator is heading to 0. So now I'm in the form to use L'Hopital's. So to use L'Hopital's, we're going to take the derivative of the top and the derivative of the bottom. So I'm going to rewrite this. So the derivative of the top is negative x to the negative 2 over 1 plus x to the negative 1. And the derivative of the bottom is going to be negative x to the negative 2. So this is really this guy. And then when I do keep, change, flip, you're going to see how I'm going to be able to cancel that negative x to the negative 2. So I'm really looking at the limit as x goes to infinity of 1 over 1 plus x to the negative 1, which is 1 over 1 plus 1 over x. And as x gets larger and larger, that's going to 0. So this is really heading to 1. Okay, but we're not finished because we said all this was equal to the ln of y. So the ln of y is equal to 1. And now we need to solve it for y, because remember we said in the beginning that y was going to be equal to that limit. That was our first step, setting that equal. So how do I solve it for y? Rewrite it as an exponential function. So this is going to be e to the first is equal to y. So this limit is actually equal to e. Okay, let's look at another example. We want to take the limit as x approaches 0 from the right. So if I look at what's happening here and what form I'm in, sine of 0 is going to be 0 as x gets close to 0 from the right, and x is going to approach 0 also. So we're in that indeterminate form 0 over 0. Again, this is where we're going to have to set this equal to y, and then we're going to take the ln of both sides. The ln of the limit is the limit of the ln, so I am switching that order. And that's going to allow me to bring that exponent to the front. And then we're going to do a rewrite. Now, to understand why we had to do that rewrite, it's going to help if we look at that graph. We know that as we approach 0 from the right, x is going to head to 0. The question is, what's happening with that ln sine of x? So let's graph that in Desmos, and we'll be able to see that there's a vertical asymptote there. So as we approach 0 from the right, you can see we do have that vertical asymptote. Everything's heading to negative infinity. So this is a 0 over infinity form, which means we've got to do a clever rewrite. So now I'm going to think about this as the ln of the sine of x over x to the negative 1, because this is in the form infinity over infinity. And now I'm in a place I can do L'Hopital. So I'm going to take that derivative of the top and the bottom separately. Ln of u is going to be du over u. Over the denominator, it's going to be negative x to the negative 2. So this is cosine of x over sine of x divided by negative 1 over x squared. And if we do keep, change, flip, it's going to be times negative x squared over 2. I'm sorry, just getting over 1. So this is negative x squared cosine x over sine x. So let's reevaluate. If I plug 0 in, I'm going to have 0 times 1, which is 0. over 0. So I'm still in the form 0 over 0. So we get to apply L'Hopital's again. So equals the limit as x goes to 0 from the right. Top is a product rule. First derivative of the second plus second derivative of the first. Derivative of the sine is cosine. I'm going to clean this up. Now I'm going to split that numerator. So I have x squared sine of x over cosine of x minus 2 times the limit as x approaches 0 from the right of x cosine of x over cosine of x. So you can see how those are going to cancel. That's why I split it, because I saw the possibility of canceling something here. So if I were to plug 0 in, I would have 0 times 0. But notice that denominator is not 0, it's 1. And this is going to be 0. Tablet's giving me issues. It's not writing some of the things I'm asking it to write. So this is going to be 0. Okay, I cannot reapply L'Hopital's because, like I said, that denominator is not 0. You can only do it if it's 0 over 0 or infinity over infinity. But remember, we said ln of y is equal to the limit, and we got 0 on this side. So if we rewrite it, e to the 0 is equal to y. And what that means is y is going to be equal to 1. So that limit for this function is going to approach 1. And then let's look at one more example. So we are in the form of infinity minus infinity. As we approach 1 from the right, that ln function, we're going to have a vertical asymptote there. Same thing here. And with vertical asymptotes, we always have unbounded behavior. So the trick when you're in this form is to combine the fractions. So we need a common denominator. So I'm going to multiply this fraction by x minus 1 over x minus 1. And I'm going to multiply this one by ln of x over ln of x. So I'm going to have 1 times x minus 1 minus 1 times ln of x all over ln of x times x minus 1. Clean this up. So now let's look at what happens. As I approach 1, I'm going to have 1 minus 1, which is 0, minus the ln of 1, which is 0. And then down here, ln of 1 is 0. And this would be 0. So I'm in that indeterminate form, 0 over 0. So let's use L'Hopital's. I'm going to take the derivative of the top. We'll take the derivative of the bottom, which is going to be a product rule. So first, derivative of the second plus second derivative of the first. Let's clean this up. And I am going to distribute this. Think about it that way. So this would be x over x, which is 1 minus 1 over x. Now, I've got some complex fractions. I'm going to eliminate those. Let's multiply the top and bottom of that big fraction by x over x, which is that common denominator. So I'm going to have the limit as x approaches 1 from the right. When I distribute, I'm going to have x minus 1 in the top. When I distribute that x down here, is x ln of x plus x minus 1. So if I plug in 1, I'm going to get 0 in the top, and I'm going to get 0 in the bottom. We're going to have to do L'Hopital's again. Derivative of the top, the derivative of the bottom. This is going to be a product rule. First derivative of the second, plus second derivative of the first. The derivative of x is 1. The derivative of 1 is 0. So I'm going to clean this up. This is 1 plus 1, which is 2 plus ln of x. So now if I look at what happens as we approach 1 from the right, this is going to go to 0. So I'm going to have 1 over 2 plus 0, which is 1/2. So there's my final answer.